For those of you who were not here last week, these review sessions are designed to help you. I'm going to try to go through the theory. Last week I did a lot about vectors and I kind of went ahead. This week I'm going to go a little ahead. And then by next week I'll pretty much be reviewing rather than previewing. So the point is that this beginning part of the course is kind of tricky, as you may have noticed. Not to say that it necessarily gets easier, but it gets maybe a little less squishy, by which I mean there's less to draw. Right now you have to do your maximum visualization. Of course, this is going to come back and be very useful when we do multiple integration and all these curves and tangents and all that sort of stuff. So anyway, this is kind of critical. What we are doing here is we are replacing numbers, which is the single variable concept that's very useful, with vectors, which is the multivariable concept. And so everything that I'm going to do so far in this little part of the course involves replacing the numbers by the vectors. Last time we saw how to add vectors and subtract them, and we saw there are three types of multiplication. And because it's sort of so important, I thought I would just begin with a little 5-minute refresher of what I did last time, and then come in. Then I will move on to that one little topic I didn't manage to cover from last week, which is the triple box product. And then I'll go on to the next part of it. So just to sort of put it in perspective, first part's just introducing the vectors. Second part is how to use them to write equations of lines and planes, and some formulas involving them. That replaces y equals mx plus b. Right? Lines are pretty important, tangent lines. In 3 dimensions we have lines and planes, and they're sort of the analog of lines. They're linear functions, they're not curvy. Right? One is a one-dimensional thing and the plane is a two-dimensional thing, but they're linear. And then quadratics were pretty important too. So we're going to do the 3-dimensional version of quadratics, which are called quadric surfaces. And you'll be covering that in class tomorrow if you haven't already yesterday. All right? So that's the sort of perspective. Once we've done that, we can move on to calculus. Okay? But we have to get those basics first. So in light of what I've just said, are there any questions that come up? Silence. Okay. Good. If you do have questions along the way, please do not hesitate to ask, even if it means interrupting. I would rather sort of just stop, go a little slower, if it will enhance the understanding. After all, these are review sessions, just seeing this for the second time. All right, so I thought I would just do a very brief review of what you can do with vectors. All right, last time I did a lot in 2 dimensions, and I said 3 dimensions follows. I'll work basically in 3 dimensions from now on. So, given a vector u, we thought of the geometry of the situation, and then we also had coordinate representations. So I'm kind of going to... So let's set up a little table, and then calculation. This is an ad hoc impromptu table here. So the vector itself, the geometry is that it is a 3-dimensional little object that has a direction and a length, but not a position. So remember, you can translate this around as long as it's still parallel and has the same length and it's the same vector. So that's the geometry. These are all the same because they are parallel and have the same length. In terms of calculating, you need to always take a coordinate basis, and the coordinate basis is normally called I, J, and K, with little lines underneath them or arrows above them to indicate that they're vectors, corresponding to the x, y, and z axes. But as you know, the axis, there's not really any right way to draw the axis, right? I mean, you could sort of say it's like this. Turn your head, make that your frame of reference, or like that, etc. So once you've picked a basis, any vector u can be written as some x coordinate. I'll call it xi plus yj plus zk. That's one way of writing it. Sometimes it's written as u1i plus u2j plus u3k to indicate that this is the first, second, and the third components, x, y, z order or I, j, k order. in either case, you also often do a shorthand as just writing it as coordinates. You say U1, U2, U3, or X, Y, Z, if you're going to use those variables. But you shouldn't think of this as the point in space when you write it like that. Rather, think of it as the vector joining the origin to that point. So if this was 5, 7, 2, you find the point 5, 7, 2. But that's not the vector. The vector is origin to 5, 7, 2. And of course, you can pick it up and move it around as long as it has the same length and points in the same direction. You're not allowed to rotate it or stretch it. All right? Okay, so that's one vector. If you want to add vectors, so that's add, the geometry was that you lay them end to end. Make V a little longer. And then, so having done that, you start at the beginning of U, and instead of going U then V, you just go straight to the end point. And that vector is U plus V. So that's the geometry there. In terms of the calculation, just add the components. So whatever, if it's 1, 2, 3 plus 5, 6, 7, you just add the x coordinates together, the y coordinates, and the z coordinates. And I did plenty of examples of these sorts of things last time. The subtraction, u minus v, well, this time you take your u and you take your v. I've picked a different v. Instead of laying them end to end, you put them at the same base point, and you draw from the tip of v to the tip of u. That turns out to be u minus v. And as a reality check, let's just check. If I go v and then u minus v, v plus u minus v is clearly u. So if you get this the wrong way around and accidentally put the head there, you'll see it doesn't work. U plus u minus v should be 2u minus v. The reality check is just to trace the arrows and make sure that they add up to the same thing. All right? And of course, in coordinates, you just subtract. So the computation's pretty straightforward. Any questions so far? All right. So that's adding and subtracting. We've done that with numbers. Now we do it with vectors. How about multiplication? Well, there are 3 types of multiplication. 3 types of multiplication. Mult1 is where you take a scalar, which is a regular old number, times a vector. And that you don't even normally write a symbol in between. So scalar next to vector. So it would look like lambda v. And just to be clear about it, we use a Greek letter normally, bless you, for the scalar. So lambda is just a number. And geometrically what this does is, if this is v, lambda v stretches it by a factor of lambda. So stretched by a factor of lambda. All right? So if lambda is negative, it points the other way. Lambda less than 0, other way. E.g., in this case, backwards. All right? Minus 1 would be exactly the same length, but pointing the other way. All right? And the multiplication in coordinates is pretty straightforward. There's the vector v, there's lambda. The product, you just multiply each coordinate by lambda. And that will do the stretching. Okay, so that's how you multiply a regular old number with a vector. To multiply, I'll call it mult2. To multiply a vector by a vector, there's a dot product. Vector dot vector. So it's a dot product, and the result is a scalar. You get a scalar, as in a regular old number. And this is, say, v dot, well, let's do u dot v. The geometry of the situation, here's your u, here's your v, I keep mixing it up. If you do u dot v, so this is the length of u times the length of v times the cosine of the angle in between them. And it represents the area, let me just make sure I get this absolutely correct. I think I know what I want to say, but I'll be very sheepish now that there's a video if I ever get these things wrong. So, no, it doesn't represent that area at all. It's given by the end of the side there, and I got into the geometry last week, so let us not talk about that. I'm getting ahead of myself here. All right, so here is the formula in terms of the geometry. And we saw that it's a sort of deficit of a hypotenuse squared minus the sum of the other two sides. So for a right-angled triangle, this is 0. Cosine of the angle is 0. But in any case, in the coordinates, u1, u2, u3 dot v1, v2, v3, you end up with, you multiply the first coordinates together, you multiply the second coordinates together, and the third coordinates, and you add them all up. All right? And finally, the third type of multiplication, mult number 3, cross v, and unlike the dot product, here you get a vector, and it only works in 3 dimensions. You cannot take the cross product in 2, 1, 4, 5 dimensions. It only is a very special 3-dimensional type of thing. Now, the geometry of this is a little trickier. What happens is, you take 2 vectors, they lie in a plane, unless they happen to be parallel, in which case you don't know what the plane is. Now, the vector that you get is perpendicular to both of them, unless, of course, they're parallel, in which case it is 0. So you get a perpendicular vector. So it's perpendicular to both u and v. How long is this vector? Well, the length is u v sine theta, which in this case is the area of the parallelogram that u and v make.
The length of u cross v is also equal to the area of
yes. Yes. So you imagine the area of this thing, whatever that number is, take a vector that long and set it perpendicular to. The only ambiguity here is the direction. And you use the right-hand rule to see what the direction is. So you sort of point along u, go to v, and then, so you start along u, go around to v, and that's up. If we reversed them, you'd have to start at u, go around to v, and that's down. The other way to do it is with this 3-prong thing. I'm doing this quickly because I did it in more detail last time. The 3-prong thing is 1, 2, 3, u, v, and then the cross product. And that actually, as long as you don't dislocate your fingers, this is the right way to do it. Well, this is the, I find it more surefire. Point u, point v, there's where the cross product goes. If it was u and v, there's the cross product. So that's another way to figure it. All right, so you use the right-hand rule to tell which one. Now, the computation of the thing's a little bit messy. You've got to use a 3-dimensional determinant. You put an I, j, k as vectors across the top, and then you put the coordinates here of u, and you will end up with some vector, some multiple of I plus some multiple of j plus some multiple of k, where you fill in the blanks. And we looked at the way to do this. For the I thing, it's this times this minus this times this. For the j thing, it's actually this times this minus this times this, but you've got to put a minus in front. And for the k, it's this times this minus this times this. I think it's pointless to remember it in terms of a formula. It's just too complicated. What you should remember it is in terms of this exact little geometry pattern. So it's a cross product. It's those two get multiplied for the I. For the j, it's these get multiplied and subtracted from each other. And for the k, it's these. And you just have to remember to put a minus in front of the j. So that's how it is, I'm afraid. And miraculously, that works out to be exactly the correct formula for a vector that is specified by that geometry. Question?
Just a quick question. For the length of the cross product,
yes.
U, is it U, length of U dot, length of V?
Well, it's the length of U times the length of V times sine theta. Maybe I should have even made a separate column for this. If you have a vector U, it's a vector. Its length, which of course is that, which to remind you is the square root of U1 squared plus U2 squared plus U3 squared, is a scalar. It's just a number. So a vector's length is just a number. So this is a number times a number times a number. So this is not even a vector thing. You could put a dot or a cross or whatever, and it would just be the regular old product. In one dimension, there's only one type of product because everything is a scalar. All three of these types of product, number one, mult number two, and mult number three, they're all the same in one dimension, although technically there's no cross product at all. All right, so it doesn't matter if you put a dot in there. Just don't think of it as a dot product in a vector sense. Another question? Did someone have one? All right. Yeah.
Isn't it minus j in the middle?
Well, okay. You might be better to write it as minus j. I mean, this could be a negative number, and then you'll get. I meant something I plus something j, but yes, it would be better to remember it like that. Less confusing. Another question.
Since the cross product is the area, what's the significance of the dot product? Is that just the length of the projection of
it is related to a projection. If V had length 1, if V is a unit vector and has length 1, it is the length of the projection. And if it doesn't, then it's multiplied by the scale of V, basically, is what it comes down to. So that's one geometrical interpretation of it. Of course, then the same thing should go for U, except that U may not have length 1, so you need to adjust by that factor. And the other way that, as I said, I mean, if you look at this hypotenuse, that's smaller than if it were a real hypotenuse, i.e. they were right-angled triangles. And so this is basically the difference between that squared and that squared and that squared. So if it was right-angled, then U squared plus V squared would equal W squared. Here, W squared is too small. If it's bigger, then the dot product is negative. So it's really the difference between U squared plus V squared and the hypotenuse W squared. That's another geometrical way of looking at it. There might be a factor of 2 in there. All right? Anyway, these things are fairly useful. In fact, this is particularly useful because it's such a simple formula. And it also, by the way, corresponds to a formula that we said that we need to remember. U dot U is the length of U squared. So the other facts, I mean, as I say, I did this last week. The other facts were that, you know, if U dot V is 0, then they're perpendicular, and vice versa. I said it. Maybe I'll just write it down. If U dot V equals 0, then U is perpendicular as a vector to V, and vice versa. So that's pretty important. That's how we're going to tell when two things are at right angles. We'll take their dot product and we'll find that it's 0. Then we'll know they're at right angles. Otherwise, they're not. And the other sort of thing is that we might as well just elaborate or re-enumerate that it doesn't make a difference which order you take the dot product, but it sure as hell makes a difference which order you take the cross product. If you get it the wrong order, you actually get the negative of the answer. In other words, if you flip the bottom 2 rows up here, you will find that you get the negative of whatever you had. before. So you've got to get the order right when it comes to the cross product. That's actually just another manifestation of the right-hand rule. Here's U, here's V, this is the direction of the thing. But if I switch around U and V, I actually have my hand here, U and V. So the vector goes the other way. So that's what that formula represents. Also, might as well enumerate that U cross U is 0. But I should put a 0 under a vector 0, because remember, the cross product is a vector. So this is the three-dimensional vector that has no length. It's not much to look at. It's just that. All right. This is, again, you can look at it in terms of area. If the vector's the same, there's no parallelogram. So the thing has 0 area. Or if you try it in the formula, you'll see everything cancels out. For example, if we look here, imagine that V is the same as U. Then this would be U1, U2 minus U2, U1. So that would be 0. And the other coordinates would also be 0. So if two vectors are in the same direction, the cross product is 0. Which is just as well, because there's no normal, there's no unique normal to just one vector in 3 dimensions. What is perpendicular to it? That whole thing sticking out. So you really need two different vectors that form a plane, and then you have the normal. All right, so that's the crash review really quick review of last time. Any questions before I do the last little bit from last time that I didn't quite manage to cover? Nope. All right. A slight extension of the cross product is called the triple cross product, or the triple box product more often, or just the triple product. And it has a lovely geometrical interpretation. So I could almost add it to the list, to this table. If I have 3 vectors, U, V, and W, which, let's say, do not all lie in the same plane. So I'm thinking of U. It's hard to draw this. I'm kind of thinking of U there, V kind of going into the board, and W going out. Although if you look at it two-dimensionally, it could just be a family of vectors down the circle or something. But try to think of this as going inside the board. Now, they would form then a box, or parallelepiped it's called. It's a figure whose I haven't drawn very well at all. Ah, hell. Put a video camera on me and I can't draw. But the good news is, put no video camera on me and I still can't draw. All I have to do is draw a bunch of parallel lines. That'll do. All right. So all the faces are parallelograms. So what is the volume of this box? Well, it turns out to be the triple box product. The formula for this, you can write, the standard form is you take U cross V and you dot it with W. Remember, you take U cross V, you get a different vector. So this is a vector cross vector gives you a vector. Dot it with W and you will get a scalar. You get a number. But we're going to take absolute values of it because it could be negative and we don't want the volume to be negative. So, for someone? Nope. All right. Maybe even another one back there. I don't think it would be in the way. Or you could just take a phone call. All right. So U cross V dot W is the triple box product. Now, I claim that actually gives me the volume that I'm looking for. So the reason is that U cross V as a vector, it's some vector that is normal to this. So it's sticking up, and it has length exactly the area of this. So here's my V, here's my W, and here is U cross V. Now, if I then take the dot product with W, what I get is the angle between here, so the cosine of that angle, times the length of W, which actually is the height along this direction. So this is the area, and then of the parallelogram, so area of base. And then when I do this dot product, I'm going to get the vector times the length of, so the length of this vector is the area. So I get the area times W cosine theta. And this height is the length of W cosine theta, just by geometry. So actually this is the volume. I'm not writing a formal proof of it because you don't need to know the formal proof, although, you know, it's good to see it and to understand what's going on. But in any case, this is the formula that you get. Now, because this represents a volume, there must be some sort of symmetry here. So actually, it doesn't really matter which order you write the thing in. You could write it as V cross U dot W, as long as you take the absolute values. Or you could write this as U dot V cross W. That's got to be the same thing, because it's the same volume. It doesn't matter whether you take that to be the base, or this to be the base, or this to be the base. No matter how you permute these things, as long as you take the cross product first and then take the dot product, it doesn't matter which order you do this in. It's kind of nice. If you drop the absolute values, it does matter. It does matter, because you might get the minus of the other. So actually this is even true without the absolute values, but it's not if you switch the U and V around. Now the practical way of computing, which I would try to fit here if it would fit to go in line of the with the table, is that the triple box product actually, even without the absolute values there, this is now a 3 by 3 determinant again, but it's just that determinant full of numbers. Okay? Remember, this doesn't mean the absolute value. It could actually be negative. It's just a notation for the determinant of this matrix. So now we actually have a really nice interpretation of what the determinant of a 3 by 3 matrix is. You take the vectors that are given by its rows, you draw them, and you get some sort of, you make a parallelepiped out of it, and you take its volume. So this is a volume. And you might recall from last time we looked at 2 by 2 determinants, and we decided that those were areas. In fact, they're the areas of parallelograms. So the 3 by 3 are also areas, except that they're actually volumes because they're three-dimensional. So this is a volume, or at least the absolute value of this. And this will become very useful when we do integration and we do change of variables. We will find that you need matrices, or in particular determinants, in order to do the change of variables. The substitution, the d theta or dt or whatever it is, will have to take determinants. All right, so if we remember right now that they're volumes, this will help explain something mysterious much later. All right, so actually, you know, you don't write that down very often, but it does come up from time to time, so better survey it. You have a question?
How can we use a 3 by 3 determinant and not just a determinant that you use when you multiply, when you did the cross product?
Like this?
Yeah, why not this, and then just the dot product of the result there?
Okay, so the question is, why not just take the cross product of U and V right there, and then do the dot product with W? Well, if you try it, you will find you get exactly the same answer. And the reason that I advocate this is because it saves a step. You don't have to write down two things, you do it all at once. But actually, it's not a bad thing to write that out and then dot it with W and check that you get the same thing if you do this. Just in terms of algebra, or you can pick your 9 favorite numbers and then try it. All right? So you do get the same formula. Now, one little thing, if 2 of these rows are the same, that means that 2 of these vectors are the same, and there's no solid. It's all compressed, so the answer will be 0. Even if one of the rows is a multiple of the other, again, the whole thing gets compressed. So for this to be non-zero, the three vectors have to be all in different directions. They have to actually span some space. All right. Question?
If I just triple box
Yeah.
I understand how the length of W times cosine of theta is the height, but why don't we have cosine theta in the U cross V?
U cross V actually has a sine theta, or a sine of a different theta, call it a phi, and that will give you the area of the base.
Yeah.
And the volume of any solid is the area of the base, well, any prism type of thing, or even if it's a skew prism like this, the volume of such an object will be the base times the perpendicular height. So you actually end up with a sine of this angle and a cosine of that angle. That's how it works. If you were doing the geometry from scratch, not knowing anything about vectors, this is the conclusion you would come to. So yes, there is a sine implicit in there and a cosine implicit in there, but that's how it works. All right. Any other questions? All right. So let's move on to section 12.5 of the book, and I'm going to look quite briefly, I hope, or at least I'll try to make it brief, at seven different types of problems or things we can find out, all dealing with lines and planes. So we're dealing with linear stuff. Then later comes the quadratic. Okay, the equation for a line. Let's start with this. Let's start with this. So we now have some line in three-dimensional space. Well, in order to motivate this, remember y equals mx plus b? Think of that. B is a point on the line, or 0, b. It's the y-intercept, and m is its slope. Well, let me do something like this. Let me just kind of cheat and write it like y is b plus x times m. And I want you to think of this as a point on the line, or representing the intercept, and this as the slope. So the three-dimensional version, or two-dimensional, or actually in any number of dimensions, so i.e. vectors, so in degree, the bad thing, I should say, in more than 1D. The equation is r. I'm going to call it r instead of y, because I've got x and y and z. So I'm going to call it r. It's a pretty lousy r. So the vector r is equal to some fixed vector r0 plus t times v. That's the equation of the line. And just think of it analogously as y is b plus xm. So I kind of want to think of this as a point on the line, and this is the slope vector. And just to emphasize that t is a sort of parameter here, you could write r of t instead of r. Okay, so what is the geometry of what we're doing here? We are describing the line in point-slope form. That's the standard form that we're used to. We find some point in space where the line goes through, and a vector along the line. So the line goes up and down. It doesn't actually matter how long the vector is, or whether it's backwards or forwards. Depending on the value of t, that will specify the line. And why does it work? Because t is a stretch factor. Look, here's the point on the line. If t is 0, you get that point. Here's the vector. If I take one lot of the vector, I get this point. Half the vector, that point. A quarter, a third, of any multiple of it between 0 and 1, and I'm between the original point and the point plus the vector. But if I actually multiply by 2, I keep going this way. And 3 and 4 or 3.5 or any positive number, and I will start getting that entire array out that way. What about this way? Negative values of t will give me this. T equals -1, -2, -0.5, -5. Any real number times that vector starting at r0 will flesh out the line. Okay, so you think of v as the slope vector. It's not actually on the line. r0 is on the line. So if here's the origin, here's r0, and here is v, then the line is actually that line. This is the line. R of t is equal to R0 plus tv. Again, t is a scalar. I said I was going to mostly use Greek letters, but here I'm calling it t, which is not a Greek letter. Never mind, I'm clearly not putting an underline under the t. So it's a scalar. This is a scalar times the vector. There's no dot, there's no cross, it's just a scalar multiple. Alright, so that's the equation of a line.
Could you explain just one more time why v goes in that direction?
What?
Is it just arbitrary? Or what?
Well, it depends on your point of view. If you don't know what the line is, then it's arbitrary, right? You pick any R0 and any v and you get the line. But suppose you already have the line. So suppose here's the origin. Suppose this is my line. Okay? There's not a unique choice of the R0 and v. You can choose any point on the line and then any vector along the line. So suppose you take this vector here as R0. Okay, now from here I can take any vector along this line in either direction as long as it's not 0, as long as it's not just that point. So tell me when to stop or go backwards if you like. Okay, that's an acceptable choice. R0 plus any multiple of v will flesh out that line. Right? R0 plus 1 times v gets you there. Half v gets you there. 2v minus v gets you down there. All right? Okay, so another question.
V is just a unit vector?
It doesn't have to be a unit vector. It can be any length vector at all along the line as long as it's not 0. If it's a 0 vector, then you just get that point. Now, sometimes it's nice to make it the unit vector because then you can see how far away you are from the point. But you could do that anyway, just with an extra division. So it doesn't have to be a unit vector. Another question.
Could you explain what it means when a function is parameterized, or like what a parameter is as opposed to
The question is, what does it mean for a function to be parameterized? So this is actually going back to single variable calculus in its conception. It was also going a little bit ahead in a way because we will be talking about vector-valued functions as soon as we finish quadrics, which may be later today, or it might be next time, or maybe Friday in your classes. But here's the sneak preview. Think of some curve in space, or let's not even do it in space. Let's just do it on the plane because it doesn't really matter for this purpose. So imagine that you take some curve. It doesn't even have to be a function. It doesn't have to be closed. It's just a curve. If you look at it, how do you write down the equation of it? Well, you could write y equals a something function of x, or sometimes it could be x squared plus y cubed equals something. That's an implicit version. But if you imagine a little snail moving around and leaving a slime trail, lovely image there, and you actually watch this is the slime trail once it's finished, but if you actually watch the snail moving, then you can see where it is at time t. So at different times it might take a rest over here and then go a little faster and then a little slower, and it maps out. At time t, you can write down its coordinates as x of t, comma, y of t. So both the x and the y are functions of another variable. In this case, I call it t, and think of it as time. It's not a bad sort of way of thinking of it. And that tells you where it is at any time. So parameter just means all the coordinates are written as functions of some other variable, and therefore gives you not only the mapping, the picture of the curve, but in a way how it's drawn. So you can tell whether the snail did this or this. Probably not this, but it's a snail, but you get the idea. So in this particular case, different choices of R0 and V can give you the same line, right? You asked me, you told me when to stop and all that sort of stuff. We could have picked R0 there and V down there. It will give you the same line, but it's a different choice of parameterization. So the T here is a parameter, and different values of T, you get different points on the line. For all the different values of T, you get all the points on the line. All right, so that's a crash course review of what it means to parameterize. Later, as I said, we'll be doing a lot with parameters, so if you didn't get what I said then, you will no doubt get it later just by virtue of seeing so many hundreds of examples of curves. And the formula for r of t, just by taking it as r0 plus tv and doing this by coordinates, you will find you get x0 plus tv1. Well, let's do it in two steps. You get x0, y0, z0 plus t, v1, v2, v3. Don't ask me why the textbook decided to use x, v, z, x, y, z, and then v1, v2, v3. I'm sure it made some sense to them. The first coordinates, x0 plus t, v1. Then y0 plus t, v2. And z0 plus tv3. So actually, each of the three components is a line in t. It's a y equals mx plus b, or b plus x m. So each of these is a line in t. And I guess that's not so surprising. Here's a line in space. If you just forget about the z-coordinate and just project it down to the flat plane, it's still a line. If you project it onto, say, the blackboard, it's still a line. Or if you project it onto some plane like this, it's still a line. Question?
R0 is a point. How can it be a vector?
Oh, that's a good question. When I say it's a point, think of it in this sense. You pick a point on the... you've caught me out here. I was being imprecise. It is the vector joining the origin to a point on the line. So, yes, vectors need to be, if you're going to call it a point, so, in common mathematical terminology, you say this point on the line, and you call it a vector, and implicit in that is the idea that the vector joins the origin, wherever it is, to that point. So, if I ever say, let the vector r0 be a point on the line, I mean, and I should say, a vector joining the origin to that point. Yeah. All right, any other questions? So there's not much to this, in the sense that there's not a lot of, there's not a lot new other than it's three lines in a parameter together. But in order to put this in perspective, does someone want to just call out three numbers?
1, 2, 3.
Oh, 1, 2, 3. Okay. How about three different numbers?
-3, 4, 5.
Positive 4?
Sure.
Okay. So what is the line joining? What is an equation for the line joining these 2 points in space? That's the question. I'm sometimes not going to write down what is the equation of the line. I'm taking you to write down if you want to make sense of your notes. So what is the line? What is an equation for the line joining these 2 points? Okay, so do you want to answer the question, or do you have a question about the question?
Answer the question.
Please. How would you do it?
1 minus 4t.
Okay, I agree in principle, but we need to show some working. So, right, so what we want to do is, remember, we need an R0 and we need a V. Okay, so we need a point on this line, or at least a vector joining the origin to that point. And I believe you want to take 1, 2, 3, which is fine. You could also take that, or you could be perverse and try to find another point, but that would be silly. So let's consider this to be our R0. Yep, it would work equally well both ways. You'll get a different answer. It will look different, but it's just a different parameterization of the same thing. So a different snail mapping out the same path. In fact, the snail will be going backwards probably if you continue.
What are we looking for?
We are looking for an equation of the line to these points. Here's a point. Here's a point. There's a line that goes through them. What is its equation? All right? So we need a V. This is not the V. Look, here's one point. 1, 2, 3. And the other point's out here somewhere. -3, 4, 5. So there's the vectors. But what we really want is this line. So if this is our R0, this vector here, then our V had better be here, or somewhere along the line. But the V is going to be the difference then between the last point and the first point. So I'm going to let v be equal to minus 3, 4, 5, minus 1, 2, 3, which is negative 4, 2, 2. You just subtract the components. Minus 3 minus 1 is negative 4. 4 minus 2 is 2. 5 minus 3 is also 2. So this is our v. So very simply, the line is r, or a parameterization of that line. So a snail starting here and moving along there. And if we actually reversed the camera or reversed the tape, we would find that backwards it was moving along there before we started watching. So we will find that it is 1, well, let's write it as R0 plus TV, which is R0 is 1, 2, 3, plus T times this vector, minus 4, 2, 2. And that's a fine answer, but you can also do what the gentleman was going to tell me, or started to tell me, and just combine this into 1 minus 4t, 2 plus 2t, and the last one is 3 plus 2t. So sorry to cut you off, but I needed to show the working. All right, so to find the line through 2 points, pick one of the points, take the difference between the other point and that point as your v. The first point is the R0, and then just plug it into the formula. Okay, does anyone have any questions about that? If you do, start asking. We'll save a few seconds. So the question is, if you're going to graph this, so suppose you were given this, 1 minus 4t, comma 2 plus 2t, comma 3 plus 2t, how would you graph that? Well, I would say you put in some values of t. Who asked it was you? Yeah, so try t equals 0 first and you'll get the 1, 2, 3. Try t equals 1, t equals minus 1, you'll see it's a line and then you can just draw the line. Alright, by the way, the reverse question would be, look at this formula and tell me what is the slope of the line and what is a point on the line. To find a point, you put t equals 0. To find the slope, you only look at the t part. Minus 4, 2, 2 is a vector along the line. Alright, now how would you tell if two lines are perpendicular? This is not actually a question in the thing, but suppose I give you 2 lines, 3 plus 7t, 2 minus t, 3 plus 5t, that's one line, and the other line looks like this, 8 minus t, 5, 6 plus 4t. How would you tell if those lines are perpendicular? Now, they may not even intersect, because there's 2 lines, but nevertheless, I'm thinking that we can maybe just... You have an idea, but you already answered. Does anyone else have an idea? Yes?
You take the 2 v's and use graph dots.
Yes, let's take the 2 v's. A v for this one, a slope vector, is given by 7, so it's the coefficient of the t's, 7 minus 1, 5. And the slope, let's call that v1, and the slope for the second line, v2, is minus 1. There's no coefficient of the t here, so that's 0, and then 4. So the angle between the lines is given by... We can actually find the angle between the lines were they to intersect, or if we shift them so that they intersect in a parallel fashion, by the formula V1. The first, this is not a component, this is just, maybe I should call it W, I don't know. This is just the first one, and this is the second one. There's nothing mystical about the parentheses there. Divided by their lengths, or product of their lengths. So this is the angle, the cosine of the angle. So we just take the dot product. It's 7 times minus 1 plus 0 times minus 1, 0 times minus 1 plus 4 times 5. And then we kind of need the length. So So I just took the length of each vector by taking the sum of the squares. So if we work this out, we get 13 over the product of 49 plus 25 is 64, but this will be root 65 because of the 1, and this will be root 17. This is not particularly pretty. That's the cosine of the angle between the vectors that describe the lines. Did I make a mistake? What's wrong? 75. Thank you. It's 49. Yes, 75 indeed. Okay, so it's still a nasty number, and moreover, it's not 0. So the lines are not perpendicular. These lines are not perpendicular. And what's more, if we really wanted to work out the angle between them, so remember, they don't have to intersect, but we can drop them down parallel so that they do. And this is the theta. We now know the cosine of that angle using the formula. Question?
You have to stop at the dot product.
I'm sorry?
You have to stop at the dot product if you realize it's not 0.
If the question was, yes, just to find the angle between, to see whether they're perpendicular, then as soon as you just take the dot product, you actually don't need to divide by these things, because if it's not 0 on the numerator, it won't be 0. All right? But if the question was to find the angle, you would have to do that equation and then take inverse cosine. Yeah?
Is it possible to do the same thing just using the R vectors? I mean, I understand why you're using the V vectors because of the vectors that are...
It is not possible to do the same thing with just the R vectors. In particular, the R vectors have almost nothing to do with it. As you see, I shifted the line here, which already changed the R. Basically, what you're saying is, if you do the R vectors, then actually all you know is points on the line. So here's two lines. Think of a line through this point and a line through this point. I'm not going to tell you anything else about the lines. What's the angle between them? Right? It could be anything. I mean, there's too much freedom there. So in some sense, the R is not as important as the V. Right? If you change the R, as you move the R, you get a bunch of parallel lines. If you change the V, then this moves the line, but they're through the same point. So that's how the freedom works of this thing. All right, so that's the first little one. Now let's try to polish off some of these other things. So that we'd better have a distance formula. So what's the distance from a point to a line? This is the second thing, is how to find the distance from a point to a line. Okay, so you've got some line, and you've got a point not on the line. What you want is to find the perpendicular, and you want this distance here. So how are you going to find that? Well, suppose that all you know about the line, this point is S in the sense that there's an origin somewhere, and we have a vector to S. Okay, but we don't know what this distance is. We don't know anything about it. Instead, we know some point on the line P, in the sense that there's the vector P. And we consider the vector PS all right. We also know a velocity vector V, which could go in either direction and is certainly not the right length. So if it were the right length, then everything would be nice. Instead, what we want to do is consider theta, and what we actually want is PS sine theta. That's the value that we're looking for. So how are you going to get the sine? You're going to use a cross product. So all we need to do is write down that the distance is the cross product of PS with V. Well, that can't be right. First of all, it's a vector. It's not a scalar. So we've got to take its length. Right? What is that? Well, that would be the length of PS times the length of V times sine theta. But we just want PS sine theta, so we actually have to divide by the length of V. So that's the lightning fast derivation of this formula. We want PS sine theta, so we kind of take the cross product, take its length, and divide by V. And it might be worth just writing that down. So this is PS times V sine theta divided by V they cancel out and you get the length that you're looking for. So the beauty of this is that given a line, P is the point on it, which is really R0, and the V we already know. So if we have the equation of a line, then this formula is pretty easy to apply, especially if you remember it. If you don't remember it, you're going to have to derive it, and that could be a pain in an exam. I'm a practical sort of guy. There's a lot of formulas here, but your memory is probably better than the derivation skills under pressure. It depends on you how much you can cram in there. There's a lot of formulas at the beginning, not quite so many later on. In principle, I would hope that everyone, given enough time and effort, could derive any of these things, but in a final or a quiz or a midterm is not really the time to do it. Question?
Is it the same as finding the unit vector for V and then crossing with PS?
Yes, if V were a unit vector,
Yeah.
then the denominator is 1. So yes, then it's just that, if V happens to be a unit vector. But you can see that from the formula directly. So here's an example. Take our previous line. Consider the line which we wrote down as 1 minus 4t, 2 plus 2t, 3 plus 2t. And my question is, what is the distance from, say, 1 minus 1, 1 to this? Maybe I won't do 1 minus 1. Let's just do 1, 1 minus 1 to this line. All right? So the first thing you have to do is dissect it. And the easiest way to do it is just to R0 is 1, 2, 3. You set t equals 0. And take V then to be minus 4, 2, 2. That's not the only choice, but that is the likely choice. So this I'm thinking of as S, and this I'm thinking of as P. So the vector from P to S, although this would also work if you went from S to P. So from P to S, I take S minus P. And you get 0, minus 1, minus 4. And here's my V, so I just whack out the formula. So the distance is PS cross V divided by the length of V. So the length of V, well, square root of minus 4 squared plus 2 squared plus 2 squared. We'll worry about that later. We're going to do take this cross product. So we need IJK, and we're going to put in the PS, which is 0, minus 1, minus 4, and then we'll put in the V vector, minus 4, 2, 2. And unfortunately, this will be a vector, so we're going to need the absolute value of this. I don't know a better way of writing this. This is the length, or the absolute value. No, it is the length. So this is the determinant on the inside and length on the outside. It looks pretty ugly. But now we have to do a computation. Well, 4 squared is 16, 20, 24. So 1 over root 24 times the length of some mess. Okay, I minus 2 minus minus 8 is 6. J, 0 times 2 minus minus 4 times minus 4 would give me negative 16, but need minus because the J. And then the K, 0 minus 4 is negative 4. And so we get a bit of a mess. We need the length of this vector. So it's 6 squared plus 16 squared plus minus 4 squared over root 24. And surely that simplifies to something units, but you fill it in. I'm not going to waste time doing a simple calculation there. Okay, so it's not such an easy computation. You have to compute a cross product, but that's life. Any questions about that example?
Distance is just the value, it's the length of PS, right?
The distance? No, not exactly. Let me just show you what's going on. The line looks like this. Here's my P. Here's my V. So the line is actually here. Okay, so this is the origin. S is some other point over here. The number that we have computed is this length right there. PS is this. So the cross product with the V has allowed us to find that perpendicular distance there. Okay, any line, no matter how it's oriented in space, and any point not on the line perpendicular to it.
We're finding.
Wait. Sorry?
We're finding PS sine theta, right?
Yeah, we're finding PS sine theta is the other way of looking at it. Where theta is the angle between PS and V. A question up the back.
How can you tell the difference between when you're trying to find the determinant of something and you're trying to find the absolute value and when you're trying to find the length of it? They're all
Okay, so the question is, how can you tell the difference given the symbols as to a determinant, the absolute value of a number, and the length of a vector? So it all depends what's inside those things. If it's a matrix, such as in the interior one there, then it will be a determinant. If it's a vector, it's the length. And if it's a number, it's the absolute value. So it depends what you're trying to do.
If you got it on a cross product, the cross product will give a vector.
A cross product is a vector. So if you have it around a cross product, it's the length of a vector. But if you have it around a dot product, the dot product is a scalar, and then it's just a regular old absolute value. So it all depends what's inside the thing. Unfortunately, here is a matrix, so it's a determinant. I know because there's vectors in there, I will end up with a vector, and so this will be the length. But in practice, it doesn't really matter, because when you're about to take the length, just see what it is, and you'll know what to do. It's very, in some sense, you can't get, it looks confusing, but you can't get it wrong, because you won't be able to apply the right formula unless you see what's inside there. So, question?
Theoretically, I can go around just a long way and just calculate the theta with the dot product, not with the dot product, but with
The question is, couldn't you calculate theta probably with a dot product? The answer is yes, but it turns out to be really messy, and you'll find that this is still quicker. Because otherwise you'll have to take the sine of an inverse cosine. And you remember how that's messy from trig substitutions, right? There's better ways of doing that. All right. So any other questions about the distance formula that I just did? Unfortunately, there's 5 more of these things to go. But they maybe get a little bit easier. So the next thing I want to look at is the equation of a plane. So surely a plane is nicer than a line. I mean, it's not as nice, but it is actually nicer. Consider this equation. AX plus BY equals C. Just from regular math. Single variable. That's a line in general position. That's just a line. Well, the equation of a plane is very similar. Suppose that I have some plane that I want to represent. Suppose I have a vector that's in the plane, in the sense that I no longer care where the origin is for the moment. There's a vector in the plane, and here's a normal in the plane, out of the plane. Well, what do you know about that? What can you say about those two vectors? Yes, they're perpendicular. So that means their dot product is 0. So if the normal is n, and let's suppose the plane is through the origin for a second. Well, then any vector on that plane is in the plane. What? Then we know that n dot xyz is equal to 0. So this means that the equation of the plane through 0 is n1x plus n2y plus n3z equals 0. So that's a plane through the origin with normal n1, n2, n3.
You have to assume that it goes to the origin.
We don't. Oh, in order to say this? Look, that definitely goes through the origin. X, if you put all x, y, and z equals 0, it goes through the origin.
Right.
So this has to go through the origin. What happens if you change this number 0 to some other number? You will just get a parallel plane. The planes can stack up along the direction of the normal. They all have the same normal. So basically, then, the general equation of a plane looks like this. AX plus BY plus CZ equals some number D, which doesn't necessarily have to be 0. And the prescription is that given this equation, a normal vector, not necessarily a unit normal, a normal vector is immediately readable off as A, B, C. Those coefficients form a normal to the plane. Not along the plane at all, it's perpendicular to the plane in 3 dimensions. And some point on the plane is given just by solving. If you want to find a point on the plane, you kind of just solve for what x, y, and z have to be given D. So actually, you could just pick x and y being 0 and find this point. Or if you're given a point on a plane, so suppose in the other way, given the point x0, y0, z0, and the normal A, B, C, then you just write down AX plus BY plus C equals D. And we know A, B, and C. The question is, what is D? Well, D is what it... Oh, thank you. There's a Z here. D is what it has to be by plugging in what the point you should know. So D must be AX0 plus BY0 plus C Z0, which is just some constant. So let me put this in perspective by looking at an example. All right. Suppose we want a plane through 1, 2, 3 with normal -3, 4, 5, those two vectors from earlier. Okay, so this is a plane that goes through the point 1, 2, 3 and has a normal pointing off in that direction, -3, 4, 5. So the plane's going to look something like this. Not a great picture, but you get the idea. So because we know the normal, the plane must be -3x plus 4y plus 5z equals something. And now we use this data to find out what D is. Plug in 1, 2, 3, and you get -3 times 1 plus 4 times 2 plus 5 times 3 equals D. And so this is -3 plus 8 is 5 plus 15, so D is 20. So the equation is -3x plus 4y plus 5z equals 20. Okay, another way of thinking about this is -3, 4, 5 dot x, y, z equals 20. So you're looking for all the points in space, or the vectors connecting 0 to the point, whose dot product with -3, 4, 5 is the constant number 20. That will flesh out a plane, as it turns out. All right? Question?
Why are you doing dot product when the normal is perpendicular? Why?
Because the dot product is 0. The dot product, so think about this example over here. The normal is perpendicular to everything in the plane. So if I take the dot product, I get 0. If I then shift the plane up, I might get 20 for every point in the plane. I get the same dot product. All right? Does that make sense? If you did the cross product, you'd get a different number for different vectors in the plane. The dot product is the way to analyze perpendiculars. All right? The beautiful thing about normals is, see, if you have a plane, there are many different vectors in the plane, but there's only one normal direction. It's positive or negative. So that kind of describes the plane. I say, here's the normal, and then you just have to tell me which slice along it that you want. Question?
Will they always give you a normal vector for you to be able to figure out the plane, or are they going to give you...
Well, they can be quite tricky. I mean, I don't like to suspect what they do, but, well, for example, here's something that I guess it's what we might do. I'm part of the they somewhat, so it's a gestalt entity. What can I say? Suppose you want to find a plane through 3 points. That's an example where they wouldn't give you a normal vector. So let's consider the plane through the points 1, 1, 0, minus 2, 0, 0, and 1, 2, 3. Okay, so how would you find the plane through those 3 points? I got to get up to quadric surfaces somehow. How would you find the plane through these 3 points? Okay, so what's your idea?
You would find the two vectors based on those 3 points.
So let's find two vectors that sit inside. Let's take this pair and this pair. So vector u is going to be minus 2, 0, 0, minus 1, 1, 0, which works out to be minus 3, minus 1, 0. So that's a vector that sort of lies along the plane. Another vector v could be this and this combined. Actually, let's do this and this combined because it's probably a little simpler. Minus 2, 0, 0, 0, minus 1, 2, 3. And you'll get negative 3, negative 2, negative 3. So those are two vectors that lie in the plane. Here's the plane. So now what do we need? We need the normal. So they didn't give us the normal. So we're going to have to take the cross product, as you say, to find a normal. A normal, not a unit normal, but a normal is given by u cross v, which unfortunately we have to whack out the ijk thing. So how many i's do we have? 2 each. Well, okay. Sorry. Minus 1 times minus 3 is 3. Subtract 0. Okay, so you get 3i. So I was wrong. J, we're going to get 9, and then a 0 there, but there's a minus for the j. And how about a k? K, we're going to get 6 minus 3 is 3. Okay, so we found a normal. It's 3, minus 9, 3. And now we are in very good shape because we know a point. Actually, we know 3 points which are on the plane. 3x minus 9y plus 3z equals some constant d. And to find the constant d, you can pick any one of these 3 points and plug it in. For example, if we put in minus 2, 0, 0, we get 3 times minus 2 equals d, because all the other two components are 0. So if I haven't made a mistake, which is perhaps improbable, I get d is minus 6, and there's the equation for the plane. Now, as a reality check, we put in minus 2, 0, 0. Let's try the other ones. If we put in 1, 1, 0, we get 3 minus 9 is negative 6. And if we put in 1, 2, 3, we get 3 minus 18 is minus 15, plus 9 is minus 6. Wow, it is the right equation. It goes through the 3 points. Question?
Can we then reduce that?
Can we then reduce that? Yes, we probably should reduce it. Divide by 3. I did not even notice. I was so glad I got the right answer. Of course, this is the correct equation. This is a more stylish way of writing the same equation. Divide by 3.
Does it say 3x minus 2 equals d?
3 times negative 2. I just plugged in minus 2 there. Yeah, my x's almost always look like that. But this could be a cross product, but it's not. 3 and minus 2 are numbers. Any other questions? All right, so we know about planes, and then there's just a few little bits of bookkeeping that we have to be able to do. So the fourth thing is how to find the intersection of two planes. Yes? Okay. To understand the intersection of two planes, well, the planes could be parallel if they have the same normal. Right? Write this down. If two planes have the same normal, or the normals are in the same direction, then the planes are parallel. But otherwise, they intersect. So, how would you find the intersection, or what do they intersect in? First of all, they intersect in a line, if they do intersect. two planes that are not parallel intersect in a line. So naturally, we want to ask the question, if I give you two planes, then what is the line that they intersect in? So what I'm going to do, each consider this plane and some other plane okay, so that's two planes right there. And I want to know what is the line that they intersect in. And if I've done it correctly, they won't be parallel. Alright, so how do you find this? Well, here's one plane. There's a normal, n1. Here's the other plane. There's the normal, n2. The line we're looking for lies in both planes. So it's perpendicular to both normals. So the line of intersection is perpendicular to both the normals. Well, given two vectors, how do I find a perpendicular that's how do I find a vector that's perpendicular to them both? Cross product. So I need, i.e., I need v, my direction vector at least, is going to have to be the cross product of the normals. Well, the normals are fairly easy to write down. It's in my ijk thingamajig. I take 1 minus 3 and 1, and then I take 0, there's no x coordinate, 1 in front of the y, and a minus 1 in front of the z. And so, if I work this out, I get 3 minus 1 is 2. There's the 2i. J, I get minus 1, but of course there's a minus, so it will be plus 1. As for the k, I get 1 times 1, and that goes away because of the 0. So we've now found, I haven't finished the example yet, I have now found a vector that goes along the line. That's a slope vector v. But what else do I need? I need a point on the plane. So what I found, just in this diagram, is I found a vector v that's along here somewhere. But that doesn't anchor the line. It just gives me the direction of it. I kind of need to anchor it. So I need an R0, so I need to find in both planes. I.e., we just need some point that satisfies both those equations. X minus 3, y plus z equals negative 6. No, negative 2. And y minus z equals 4. So we need a simultaneous solution. It doesn't. There's infinitely many, but we just need a solution. Well, the easiest thing to do is pick one of the coordinates. Be careful. Well, you could pick any of the coordinates, but it might be simpler to pick one that appears in both the equations. So let's just pick z, for example. E.g., set z equals 0. See if we can find a solution with z equals 0. So if we do, we get y equals 4 from the second equation. And from the first equation, we get x minus 3y equals negative 2. So x is equal to 3y minus 2. We already know y is 4. So this is 12 minus 2, which is 10. I.e., x equals 10, y equals 4, and z equals 0 is a solution to both those. So 10, we can take R0 equals this. So our line is now R of t is equal to R0, which is 10, 4, 0, plus t times this vector that we just found, 2, 1, 1. Okay, so just to remind you, unfortunately the camera will have to come over here for a second if you don't mind. That vector we found in the first stage of it was 2, 1, 1. That's our v. So that explains back over here where the v came from, where that 2, 1, 1 came from. And then you could write that if you want to as 10 plus 2t, comma 4 plus t, and then just t. Again, there's no unique solution. There's a redundancy in the choice of this. Any parallel vector will do. And there's a redundancy in the choice of this. Any point along that solves that simultaneously will work. So as long as you write down some correct parameterization, it's not a unique solution. All right, any questions about that example? Okay, find the intersection, take the cross product of the normals. I don't know. These things are fairly technical. They will be examined much more in the quiz and in the midterm than in the final, but it's still fair game for the whole semester. Question?
So I just like make sure that, so the first point is the intersection, the second is the cross product of the normal?
Yep, the first point is intersection. As you see, I just picked z equals 0. I could have picked y equals 0, or even x equals 0, and solved simultaneously for the other two. I could have put z equals 1 and found, you just pick one value for one of the coordinates, and then solve simultaneously for the other two. And you'll find a point on it, unless you're unlucky. If you're unlucky, then you won't be able to solve it because the line is vertical or something like that, in which case, try a different coordinate. Question?
How do you know that z equals 0 or something is in the x, y, and line?
Well, you don't, but you see, if you try it, and then you find what x and y are, then you can see that it's going to work, it's going to satisfy both of those equations.
But couldn't the line just like pass the point? It could go all over.
The line could avoid z equals 0, I agree. If it's a line that's parallel to the z equals 0, then it will avoid it. And that's when I said you're unlucky. But it can't be parallel to everything. So if you try x equals 0, then you'll be okay. Or maybe it's parallel to both those planes, but you see, then it would have to be y, then you put y equals 0. One of them equals 0 will work. And most of the time, any of them equals 0 will work. All right? Any other questions? All right, let's go on to the next one. How about the intersection of a line with a plane? Line intersect plane. We ought to know how to do that. So here is a plane, and here's some line. We're looking for a point, or a vector if you prefer, a point in space where, bless you, where the line intersects the plane. Well, there's not much to say about this because it's really straightforward. All you have to do is solve simultaneously. So for example, where does 3 plus 2t, 1 minus t, 4t, that's a line. Where does this line intersect the plane? Let's just keep the same plane. What the hell? X minus 3y plus z equals minus 2. Where does that line intersect that plane? Well, this is x, this is y, this is z. So you just plug it in. You get 3 plus 2t, that's the x, minus 3 lots of y, 3, 1 minus t, plus z, 4t equals 2. And now we should be able to solve for t. Oh, did I make a mistake? Oh, negative 2, thank you. I did make a mistake. All right, so what do you get? You get 3 plus 2t, minus 3, plus 3t, plus 4t. So I think we have 9t, and we have 3 minus 3, which just cancels. So 9t is minus 2, i.e. t is negative 2/9. So we now know the value of the parameter. But with the orbital point, let's plug it back into the line. So the point is 3 plus 2 lots of 2/9. 1, oh, it's negative 2/9. 3 plus 2 times negative 2/9. 1 minus negative 2/9. And 4 times negative 2/9. It is 23/9. 23/9, 11/9 minus 8/9. Okay, so we don't have to do anything fancy with dot products, cross products, or anything. You just plug it in and solve. So that one was not so bad. Any questions about finding the intersection of a line and a plane? See how much nicer it is than two planes?
What if you just had a line on the plane instead of the plane?
Okay, there's some problems that could happen. One problem would be, imagine the line was in the plane. What would the point be? Well, if you did that, you would find that the t's all cancelled out, and you get something like 3 equals 3. So in some sense, any value of t would solve the equation, and the line would be in the plane. What if the line was parallel to the plane and didn't intersect it? Well, then you get something like 3 equals 2. The t's would also cancel out. And that can't be true for any value of t, so that it wouldn't intersect. So this all comes out in the wash. You just have to not panic and interpret it correctly. If you get 3 equals 2, you probably don't have an intersection point, or you made a mistake. If you didn't make a mistake, you have not proved that 3 equals 2. You have just said that there's no value of t for which 3 equals 2, which is not quite the same thing. All right, any other questions about that? All right. We did the distance from a point to a line. We have to see how to do the distance from a point to a plane. But it's easier. Planes are actually easier than lines in a way. So we have some plane, blah, and we have some point not on the plane, which again we're going to call S. Imagine that we have a point P on the plane in the sense that we have a vector as before. And what I want is to drop a perpendicular from S down to the plane. So this is perpendicular in every direction. And what we want is this distance here. That's the actual distance that we want. Well, we do the same sort of trick. We consider the vector PS, which looks like this. So this is the vector PS. And if you look at this angle here, theta, you will see that this time the length is equal to PS cosine theta. Last time it was sine. It's length of PS times cosine. So this time we want a dot product, not a cross product. When we're doing a point to a line, we used a cross product. Now the thing is, though, we need the dot product of something with something. Well, this is the something, which is the normal. So this is the normal here. So we actually want PS times the dot product with n. Now that, of course, could be negative depending on the directions of these things. So we'll take the absolute value. But the problem is that we want PS cosine theta. We don't want the length of n. And this is PS times the length of n times cosine theta. So just as we did before, we'd better divide by the length of n. I'm a mess. N is the normal. PS cosine theta is the length along the normal that we want. So they're sort of the same, but one is the length. N actually could be longer or shorter. It's just that's the direction of n. But it doesn't matter what it is, because you see we have an n, we're going to have to divide by the n. Let's underline it as I've been doing. So this is the distance. Okay, so bless you. So you see that the other formula, the distance from the point to the line, was PS cross V, where V was along the line, divided by the length of V. This is exactly the same formula, except n is now the normal, and we're using a dot product instead.
So we would just choose some point on that plane?
Well, right, so you're going to have a point on the plane. So for example, okay, let's take this same plane here, x minus 3y plus z equals minus 2. And now I'd like the distance from the point 1, bless you. I like the distance from the point 1, 1, 1 to that plane. So you have to recognize it's a plane, not a line, because otherwise you'd be using the cross product. And I want the distance from that point to that plane. So how am I going to find it? Well, what I will do is consider the normal that I'll use is 1 minus 3, 1, as before. I'm just reading off the coefficients. And I do need a point on the plane. I need a point on the plane. Well, how am I going to do that? Well, again, this is a case where you can let any of the coordinates be 0. In fact, what's a point on this plane that you can just easily see? 0, 0, negative 2. Or it could be negative 2, 0, 0. You can let two of the coordinates be 0 and see what the other one has to be. Let's just take 0, 0, negative 2. Okay? That's one example. But as I said, you could use any of the coordinates being 0, or you can futz around and try to find some solution. You have 2 degrees extra of freedom that you don't even need. So let's take that. So that's our P, and this is our S. So the vector P to S is equal to 1, 1, 1. That's the S coordinate minus the initial coordinate, 0, 0, minus 2. So I get 1, 1, 3. So there's my PS. So the distance is equal to the absolute value of PS dot the normal over the length of the normal, which is 113 dot 1 minus 3 1. Everything's 1s and 3s just by accident over the length of the normal. So this works out to be 1 times 1 is 1. 1 times minus 3 is negative 3. 3 times 1 is 3. Okay, so it ends up being another formula for the collection, but very similar to the other one. So you should understand why you need one and the other. But ultimately, don't try to derive it in a quiz, is my advice. You can if you like. I don't think it's practical. All right, question.
So the n would be the normal to the plane?
N is a normal to the plane. N is always normal in this, and you can't just have a normal to a line because you don't know which one. Here's a line. What's normal? Any of these, it's normal.
And so the n is equivalent to the vertical line that we dropped down from S?
It is along the, N is along that direction, but it's not necessarily the actual correct length. So you need to kind of scale it by doing this division here. All right? Okay, the last thing. Angle between planes, but I already did it. No, I didn't. I did the angle between lines. I didn't do it, so I have to spend a few seconds. But it doesn't take long. Then I can do quadric surfaces. I know. Okay, if two planes do intersect, they intersect in a line, as we saw. So what we can do is take two lines along each plane that are each orthogonal to this line, and then consider the angle between them. So that's the angle between the two planes. Basically, just so it looks like a big mouth. Take the projection of the two planes so that they're coming out of the board. Imagine this paper here and this paper here as the two planes. That's the angle between the planes. All right, but it also happens to be the angle between the normals. So this one would be the normal to this plane. This one would be the normal to this plane. So that's an easier way to view it. So by definition, you might as well consider the angle between two planes. By definition is the angle between the normals. So that's pretty easy. You just use the standard cosine formula. E.g., if we take x minus 3y plus z equals minus 4, and y minus z equals 2, the normals are 1 minus 3, 1, that's n1, and 2 is just 0, 1, minus 1. And so the cosine of the angle that we're looking for is n1 dot n2 divided by the length of n1 and the length of n2. So we just take the dot product of those two things, and you'll find it's 0, minus 3, minus 1, all over the length of n1 times the length of n2, 0 squared plus 1 squared plus minus 1 all squared. And if you work this out, you get negative 4 over root 11 times root 2, whatever that mess is. you might as well write it as negative 4 over square root 22. So the actual angle is the inverse cosine of this, which I do not know what it is. I do not speculate. All right, so the angle between two planes, it's easy if you remember what it is. It's actually the easiest computation that we've done, apart from this one I've just erased. So that's a sort of crash course on all the different sort of types of things you can do with lines and planes. You know, we've done in basically every combination of them. And it all reduced to basically dot products and cross products. So if you understand those, you get those formulas. Any questions before I move on to the surfaces, which I really think is, I've only got 25 minutes, but I can actually basically cover it. All right. There are 4 types of surfaces that we're going to consider in this course. The first is different from the other 3. Now, I want you to imagine a graph like this. That's a circle in the plane. Radius 2. All right? What if we consider it as an equation in 3 dimensions? Well, in 3 dimensions, maybe I'll write x here and y there and z there for the perspective of it. But this doesn't tell us anything about z, that equation. So z is free. That means z can be anything. That means that you've got to replicate that circle at every height. And you get a cylinder. So if one of the variables is missing, you basically get a 2-dimensional graph that just moves up and down in a cylindrical fashion. What if you had y squared minus x squared equals 4? We don't really pay that much attention to this, but you better learn that this is a hyperbola. Sort of has a sort of circle at minus 2, well, the circle of radius 2, but it's going to be a hyperbola like this. No, it's not. That's x squared minus y squared equals negative 4, equals 4. It's going to be a hyperbola like this. How did I know that the other one was wrong? Well, the y-intercepts are 2 and minus 2. There can't be any x-intercepts because then x would have to be the square root of minus 4. So actually what I first drew was x squared minus y squared equals 4. Right, so if you'd be able to draw 3-dimensional surfaces, we've got to be able to draw 2-dimensional things like this. So you need to know how to draw these hyperboloids. If you consider this as a graph in 3 dimensions, you just draw it down here so that the y-axis is like this. Not so easy to tilt the perspective, but the y-intercepts are 2 and minus 2. And then you make it into a cylindrical sort of object by doing carbon copies. So it's a cylinder, but it's not as a regular cylinder, it's a hyperbolic cylinder, if you like. Just took a hyperbola and shoved it up and down. All right? What if the variable missing is not z, but is instead, say, x? So suppose I took y squared minus z squared equals 4. Well, let's take our same x, y, z. It looks a bit confusing. This is actually the positive x-axis, so I've kind of turned around so that x, y, z. So this is 1, 2, 1, 2, 2, 1, 2, and the negative directions go down there. Okay, so what's going on here? Again, the intercepts are at y equals 2 and minus 2, but now the hyperbola's got to go along the yz plane. So it had better look like this, and then parallel in this direction along the x-axis. So the x is the free one. And so all these lines are horizontal. So the surface is in 2 pieces. Didn't draw that well. All right, so the moral of the story with the cylinders is that if one variable is missing, it's a cylinder. So draw it in the right plane and then just shove it back and forth perpendicular. All right, so cylinder is the easy case. Before I move on to the harder cases, does anyone have any questions? No questions. All right, so we're dealing with quadratics. A general quadratic has a rather nasty form. We've got to have ax squared, by squared, cz squared. They're all quadratic pieces, but there are other sorts of quadratics. xy is actually a quadratic. So is xz. So is yz. But quadratics also have a linear piece. So we need a gx, hy, jz. Yeah. I have a friend who works with jz. There you go. Went to his wedding not long ago. All right, plus k equals 0. So there's a constant term. So that is the general form of a quadric surface. However, it turns out by doing funky completing the squares and rotations and all that, you can reduce the thing to a number of much simpler cases, and since the reduction is really for a course on linear algebra, we will content ourselves with the simplest sorts of things. So the simple sort of things is where we don't have any of these, so we're going to pretend we never have these, because in any case you can reduce them, and actually we're not going to really have these either, unless we are missing a square. So, in order to present this in sort of a systematic fashion, which in my opinion the textbook doesn't really do, I'm going to show you the three families, which are all sort of, well, I think everything can go into three families. So let's look at the simplest one. Suppose we have only squares. So the prototype is x squared plus y squared plus z squared is equal to, say, 1. This is the prototype of this. So the point is that all the squares, they're all squares, and they're all positive coefficients. So this is the first family. In its pure form, as I have it there, you're dealing with a sphere. The way that it's drawn is a sphere. This says the distance from x, y, z to the origin is 1. So you get all the points which have distance 1. It's a sphere. That's the prototype. But you're also quite likely to see a slightly different version like this. 4x squared plus, say, 9y squared plus z squared over 4 equals 1. Suppose you saw that. Well, think of it like this. This is the same as 2x all squared plus 3y all squared plus z over 2 all squared equals 1. So what does this do? Instead of x, we have 2x. So we kind of have to halve everything in order to get the same sense of perspective. So x is going to be shrunk by 2. Y is going to be shrunk by 3, but z is going to be stretched by 2. So actually, the x-intercept is going to be a half on both sides, a half and minus a half. The y-intercept is only going to be a third and minus a third, but the z-intercept is going to be 2 and minus 2, and what you'll get is an ellipsoid. So it's just a stretched out sphere. It's not a football, it's actually rounded at the edges here. So we get an ellipsoid. So it has 3 different axes. 1/2 to minus 1/2, 1/3 to minus 1/3, and 2 to minus 2. Bless you. So if you cut it in any direction, basically you get an ellipse, but they're different shaped ellipses. So it's a sphere that's been that sort of thing. We're stretching and shrinking the sphere. So the general sort of equation for this is x over a all squared plus y over b all squared plus z over c all squared equals 1, and that will be an ellipsoid. So here's the x, here's the y, here's the z, and that will have coordinates a, b, and c. Goes through minus b. It's a pretty poor drawing. Okay, so, but think of it as a sphere that's been stretched and squished along the coordinate axes. All right, what if you don't have a 1 here? What if this is like a 4? Well, you just divide both sides by it and make it a 1. All right, so that's the simplest one. Any questions about it? All right. What if instead you had x squared minus y, plus y squared minus z squared equals something? Okay, so 2 of them are positive. They're all squares. But 2 are positive, 1 negative. That's actually the only other possibility if they're all squares. Why? What if 1 is positive and 2 is negative, and 2 are negative? Well, then you multiply the equation by minus 1, and then 2 become positive, and the other one's negative. So you can always change it. What if they're all negative? So suppose it was minus x squared minus y squared minus z squared equals 1. No solution. Can't have negative squares. The left-hand side would be negative. Unless, of course, the right-hand side was minus 1, in which case you multiply by negative 1, and everything becomes positive. So everything is in one of those two, as long as everything is squares. So in order to understand this, let me consider the case where it's 0 first, then the case where it's positive, and the case where it's negative. And you will see that they're all nicely related, although the textbook, I don't think, makes much of a deal about this. So let's consider x squared minus y squared, x squared plus y squared minus z squared equals 0. Well, this means that z squared equals x squared plus y squared. So at each height, we get a circle of a different radius. When z equals 0, we just get a point. When z equals 1, we get x squared plus y squared equals 1, which is a circle of radius 1. When z equals 2, we get x squared plus y squared equals 4, which is a circle of radius 2. And in general, the radius will equal z. Unless, of course, z is negative, in which case the radius is the absolute value of z. So this is just a cone. This is supposed to be along the same lines. Again, what if you have, say, 4x squared plus y squared minus z squared? Well, that would just shrink the x by 2. So the cone, instead of having circles, would be ellipses. So since I don't have a lot of time, I'm not going to spend much time on this. I just want you to understand that having coefficients out front, all that does is just stretch different values, different axes. So in my example, just 4x squared plus y squared minus z squared equals 0. The only difference between that picture and the other picture would be that x is squished by a factor of 2. So instead of being circles, they're ellipses. So the cone is sort of fatter in the y direction than it is in the x direction. All right. I don't know how that got tilted. It's supposed to be vertical.
Will it always be equal to 0 on the right?
No. Let's look at the next case. What if it's equal to, say, 1? Well, the best way to see it is that even if z equals 0, you actually already have a circle. You already have a circle. So even if z equals 0, you have a circle of radius 1. But then, as long as z is not 0, you get an even bigger circle. What you will actually get is called a hyperboloid of one sheet. How do you know it's a hyperbola? Well, imagine you cover up the y. You get x squared minus z squared equals 1, which, as I said earlier over there, is a hyperbola. So in the xz plane, which is here and here, so this, you'll get a hyperbola. Also, in the yz plane. So this is called a hyperboloid of one sheet. And I will soon show you the connection between this and the cone. But first, I want to consider the situation where it's equal to negative 1. So if we look at x squared plus y squared minus z squared equals negative 1, now if z equals 0, we've got a problem. You can't have x squared plus y squared equals negative 1. So there's actually nothing, there's no action at z equals 0. In fact, there's no action at all until z is 1 or minus 1. So above 1 and below minus 1 is the only hope. Because if you write it as x squared plus y squared equals z squared minus 1, you'll see the right-hand side has to be positive for you to have a solution, or at least 0. So z has to be bigger than 1 or greater than minus 1. And what you'll actually end up with is circles that get bigger, but only from 1. It looks like a little bowl, and another bowl down here. But actually, if you look at how that bowl looks, again, we can think of this when x equals 0, say, we can rewrite this as z squared minus y squared equals 1. So this is a hyperboloid, is a hyperbola, as is this and this. So the bowl is made up of a revolved hyperbola. If you turn your head this way, you will see the hyperbola, and it is just revolved around the z-axis. So this is called a hyperboloid of two sheets. Okay, what is the connection between these three? Let me draw in x squared plus y squared minus z squared equals something. Okay, here's what it looks like. Here's my x, here's my y, here's the z. Okay, if c equals 0, I get the cone. So c equals 0, I get the cone. If c is positive, I get a hyperboloid of one sheet that is asymptotic to the same cone. So c greater than 0, I get hyperboloid of one sheet. Which one do I get? Well, it depends. The bigger c is, the further out the hyperboloid starts, but it still will be asymptotic to the cone. So I could get, they're all nested in. But when c is negative, I get the rest of it. I get the two-sheeted hyperbola. So c less than 0, hyperboloid of two sheets. Okay, so that's the connection between them. So if I ever forget which one it is, all I do is just pretend it's, obviously if it's 0, I know it's the cone. But if I can't tell whether it's one sheet or two sheet, I just draw in the cone and try to find one point on it, and then you can see what it is. You can see what it is. I mean, try to find a point on the z-axis, say. If there is one, there'll be 2, and then it'll be 2 sheets. If there's none, it'll be 1 sheet. All right? Now, in terms of variations, given the limited time that I have, I really want to introduce at least what the last one is, although I won't be able to spend much time at all on the ramifications thereof. What I want to tell you is that we've seen that the coefficients just correspond to stretching, right? If you just have coefficients. But in this case, there's a slight extra wrinkle, and that is, it doesn't have to be z that has the minus sign in front of it. It could be something like minus x squared plus y squared plus z squared equals 0, say. If that's the case, you have to just mentally reorient yourself and say, well, now the cone is along the x direction, so kind of the circles have to be increasing along the x direction. So it becomes sort of hard to draw. Probably best to draw the two lines first and then fill in the circles. So you get a cone along there, and of course if you had different numbers there, you'd have a hyperboloid along those ways. So be careful not only of the coefficients, which stretch and shrink the different axes, but also the order in which, be sensitive to which ones are positive and which ones are negative, because that just rotates the whole picture. Now, I've only really got a minute or two, so the third type is where one of the terms is linear, and I just kind of want to show you this, and that's all I have time for. So one term is linear. So as an example, the prototype example would be something like this: x squared plus y squared equals z. So it's two squares, both positive, or both the same sign, but not a square. Just linear. Well, the effect of this is to give you, instead of one of these hyperboloids or an ellipsoid, it gives you a paraboloid, in the sense that z equals x squared would look like this, just a parabola, and z equals, well, that's actually z equals y squared. Z equals x squared would look like this. Here's the x, here's the z, and this equals y squared would look like this, and you actually get the revolution of a parabola. So this is a paraboloid. The paraboloid is, the center is the z, so it's always the z equals x squared or z equals y squared. So if you look at it this way, you get a parabola. And if you look at it this way, you get a parabola. But the parabola, it's the point is on the origin, and the vertical is z in both directions. Now, of course, if I took 4x squared plus y squared, that would be shrunk in the x direction. So instead of these being circles, they could be ellipses. They could be shrunk. So it's actually called an elliptical paraboloid. And for my last trick, I will show you the last type of surface, and it's the most complicated, and unfortunately there's no time to explore it. But if instead you have x squared minus y squared equals z, you get something a little bit more diabolical. This is two squares of opposite signs, and z is linear again, so you know you're in for a paraboloid. So what are you going to get? You're going to get a difficult thing to draw. Is this a what?
A fourth one, or is this still under the third?
Well, this is still under the third, but it's a different type of paraboloid. So it looks like this. Z equals x squared would be a parabola where, if you think of it as y equals x squared, so it's now z equals x squared, and you're going to get a parabola that goes like this. However, so that's in the x direction. However, in the y direction, it's the opposite. Z equals y squared, you get the opposite. So what you're looking at is a parabola and another parabola, and they're at right angles to each other and in opposite directions. So it's like a saddle. The saddle is like this, but also like this. So kind of hard to draw, but the general gist of the thing is, maybe I should have done y squared minus x squared equals z. Gee, I really hate going over time, but if I don't draw this, then it's going to be a travesty. So I'm going to just cheat, because I know how to draw this, and I'm going to try to give you the very quick sketch, although there is a much nicer sketch in the textbook. So z equals y squared looks like this. Here's z. Whereas z equals minus x squared looks like that along this line here. And then the surface has parabolas along it that go down. But along this direction, they look like hyperbolas. So, like that, without the axes. All right? So that's a saddle point. It has an upward parabola in one direction and a downward parabola in the other direction, and these cross sections are all hyperbolas. Well, this is a parabola, this is a parabola, but that's a hyperbola, and that's a hyperbola. All right, so that's a survey of the thing. We'll come back to it next week, and this will make more sense after you do it in class as well. All right?